go to the cloud, and then I'm going to stop sharing my screen, and you should be good to share your screen.
Okay, let's do that. Right, can you see that?
Yep.
Good. Oh, now I'm going to hear my clock chiming. That, I suppose, should have been the signal to start. At least it's not going to chime 10, given where I am.
That is very true. All right, I'm gonna get this guy up. I think so we had this old thing that was like called tech time, which was everything like started 5 minutes after the hour, and there's still, we've done away with it, but there's still some people that I think live on what we call tech
All
time.
right. Well, before I retired, the university, Bath University, where I used to work, every lecture and class started at 15 minutes past the hour, and had done for 30 or 40 years. And the reason for that was that 30 or 40 years ago, there was a bus that arrived at the university at 10 past the hour. So that bus is long forgotten, but it fossilized its arrival in the timetable. So
interesting. I think we'll wait 2 more minutes, and then we'll get rocking and rolling.
Okay. Okay. Well, I think we've waited enough. So Okay.
guess I'll just do a quick introduction. So hello, everyone. I'd like to thank you all for attending this talk by Dr. Adrian Bowyer. And especially would like to thank the man himself, Dr. Bowyer, for agreeing to meet with us today. And so for those of you that don't know me, I'm Shane, an assistant teaching professor in electrical engineering department, and I'm instructing our open source 3D printing class this summer. I reached out to Dr. Bowyer to give this talk because I really do kind of view him as the godfather of 3D printing. And he and his team's achievements are a huge landmark in the history of this field. So I don't want to steal too much of his thunder because Dr. Bowyer has a brief presentation in which he'll kind of introduce all of his work. And so once he's done with that, we'll open the floor for questions from both the audience and myself. So without further ado, Dr. Adrian Bowyer.
Thanks, Shane. Yes, hello, everybody. And thank you for inviting me to talk with you. This is a very brief presentation. I hope that anything that's missed out, which there will be a great deal, we can perhaps cover in questions afterwards. But I just wanted to say a few words about the RepRap project, which is a project I started, and its influence, or rather how it came about and how it led to the sort of 3D printing industry that we see today in large part. Anyway, RepRap, well, first of all, what's that short for? It's an abbreviation of Replicating Rapid Prototyper, and we'll come to that. And the key thing here is not so much rapid prototyping, which is an old word for 3D printing, but the fact that it replicates anyway. So what we're going to be talking about is an open source, self-replicating 3D printer manufacturing machine. So a bit of history. Around about the turn of the century, the British government gave my university a very large wheelbarrow of cash to spend on equipment, and perhaps foolishly, the university gave quite a bit of that wheelbarrow full of cash to me to spend. And I bought a couple of 3D printers for the university. We didn't have any before. I'm an engineering teacher there. I knew all about 3D printing, but that's in a theoretical way. I'd never actually used it for anything. I knew how it worked, and I knew what the machines did, but as I say, never actually practically used it. Anyway, so we acquired a couple of machines. One cost about $250,000 and the other cost about $50,000. And that latter one was about the cheapest you could get at the time, 2002, 2003, thereabouts. And as soon as I started using these machines, I realized what an incredibly versatile way of making things that 3D printing is. In fact, it's the second most versatile method of manufacturing that we know about. We can look into that classification a little bit later on in questions if you like. But anyway, given its versatility, it occurred to me that it might be possible to use one of these machines, or at least to design one, such that it was capable of making most of the parts for a copy of itself. And this is an idea, the idea of a self-copying machine, that I've been interested in for decades and decades, right back, in fact, into my childhood. I can't pin when I first started to become interested in that. And I wasn't too interested in making something that was completely self-copying, which I thought would be very difficult. I wanted to make something that was self-copying in a sort of good enough way that it could reproduce itself. So I set about organizing a project to build a 3D printer that could print a copy of itself. And in doing that, it seemed to me that I was doing something that was potentially had quite a high impact. So I thought there was a certain duty on me to tell people that I was going to do it before I actually did it. And this was back in the time before wikis and before social media and all that sort of thing. So I got hold of my university's press department and we put out a press release. And this got picked up because it's a self-reproducing machine, and that sounded quite interesting to a lot of journalists, obviously. It got picked up by some fairly major outlets, people like the BBC, the Canadian Broadcasting Corporation, Hindu Times, a newspaper in Australia, New York Times, I think, various places. Anyway, and they all printed stories on this, having in some cases interviewed me. And one of the side effects of this was that a lot of people got in touch with me and said, oh, this sounds interesting, how can we help? And their ability to help was much enhanced by the fact that I decided to make the project completely open source. Why had I done that? Well, as I say, it seemed like potentially a rather impactful thing to do. And if you're going to have a high impact technology, then one of the effects that that can have is to create a greater divide in society. You know, there'd be people who'd have it and people who had to pay for it and therefore didn't have it so easily. Now, all right, I'd be in the first group, great. But on the other hand, it seemed to me to be a bit of a way to increase inequality, and I didn't really want to do that. And that was perhaps an uncharacteristically noble thought for me. Anyway, about 2 minutes after I'd had that uncharacteristically noble thought, I suddenly realized, if you've got a self-replicating machine, you've got to open source it. If you try and patent it, for example, what you're saying to the world is, here is my self-replicating machine, which is patented, so you can't self-copy it. That doesn't really make any sense. Now, I know that some self-copying things are patented. For example, companies patent seeds and that sort of thing. But nonetheless, to me, it seemed like the only logical thing you can do with a machine that's intended to copy itself is to let everybody go away and copy it. So we and the people who volunteered, because they'd seen the various press articles about the project, set about designing the first machine. And what you can see on the screen now is a picture of the first machine. It's the one on the left with me standing beside it. And that machine printed all the plastic parts for the machine on the right. And the bloke standing there is Vic Oliver. He's a New Zealander. And he was, I think, the first volunteer on the project after it started just with me and my research student, a man called Ed Sells. And so we made the first machine, and the first complete machine was finished, as you can see, 4 years or so after I'd had the initial idea. And I'm sure these slides will be made available to you. You'll see at the bottom right-hand corner of the screen there, there's a reference if you want to go and look up the paper on the project. Okay, so that's version 1 of the machine. That's another picture of it. The object that you can see in the CAD system on the screen is in fact a part of itself, the part of the extrusion mechanism, and the machine is in the process of printing that very part. And you can perhaps see more clearly there all the plastic bits of the machine. It looks as if quite a lot of it is not actually self-replicating in the sense that it consists of steel rods and so on. The proportion of self-replicating parts, if you ignore fasteners, things like nuts and bolts, was actually though quite high. It was about 50 or 60% of the number of parts in the machine were parts that it made for itself. Okay, and so if we go up to the present day, we now have much more advanced RepRap machines. This is just one example of the many, many descendants of that first machine. There are several hundred designs out there now, some of which are now obsolete, others of which are still being made. This is a RepRap machine called Mulbot, and everything you can see there that's red or blue or white is actually a 3D printed plastic part that the machine itself can make. So that's got a fairly high percentage of self-replication, and it prints on the transparent glass plate that you can see in the bed of the machine there. Okay, now some principles behind RepRap. As I say, the name is short for Replicating Rapid Prototyper. Rapid Prototyper was what 3D printers were called 15, 20 years ago. It was polite engineering speak. People thought that 3D printer sounded a bit journalistic. And of course, the nature of language is that the easy and simple term is the one that's come to be universally used. So now everybody just talks about 3D printer. It's important to emphasize that I and the RepRap project didn't invent 3D printing. The invention of 3D printing goes back quite a long way to 1973, 74 or thereabouts. There was a man called Win Kelly Swainson who patented the first idea for 3D printing a year or two before that date, though his patent hadn't been published. The very first appearance of the idea of 3D printing in public was as a joke. There used to be a column written in the New Scientist magazine by a man called David Jones, who wrote under the pen name Daedalus. And that little column was a series of implausible inventions, which were intended to amuse the readership. And he had the idea that you could shine a laser into a tank of monomer, plastic monomer, and where the laser beam hit the monomer, it would cause it to polymerize by photopolymerization and therefore set solid. And he said that you could move the laser beam about and print out a 3-dimensional shape in the volume of this liquid monomer. And of course, that's one of the first types of 3D printing that was actually achieved, even though he didn't think it was a serious possibility at the time. Anyway, as I say, we decided to open source it, going down to the line that says give it all away free. We put it out under the new general public license, version 2 at the time as was. And that meant that anybody who had the design files, which we also put online, of course, could make one of the machines if they had access to any sort of 3D printer, including a commercial 3D printer, of course. And as I say, we got volunteers from all over the world because it was an open source project and they thought it was interesting to work on. And at one time, I worked out that, in fact, I was running the largest research group of any engineering or science research project in the United Kingdom, with the added advantage that with all these people who were working for me, I had to pay only my research student. So not only did I have the largest research group, it was the lowest cost one. So that was working actually quite well. And it was one of the reasons why the machine became a success, because we had so many ideas from so many people all over the world. Pretty much every do-it-yourself 3D printer these days is a RepRap in some form or other, in the sense that they almost all incorporate 3D printed parts in themselves. If hobbyists go away and make their own machine, it's pretty rare these days that they make a machine without any 3D printed parts. And many commercial 3D printers are now RepRaps. We'll look at one in a moment, though there are several. And virtually all 3D printers are based in some way on the RepRap project, which, as I say, we didn't invent 3D printing. We didn't invent the type of fused filament fabrication process that RepRap uses. That was in fact invented and patented by Stratasys. But pretty much everything that's out there at the moment is actually based on all the open source material that we put out that enabled other people to get on board and make these machines. I say that Stratasys had the machine patented. One of the things that was an advantage of working in the United Kingdom and in Europe in general is that in Europe you can work on a patented technology to improve it without paying any license fees to the patent holder. That's considered a legitimate use, which you don't have to pay license fees for. As I understand it, that's not the case in the United States. If you would work on a patented technology in the United States, you have to pay license fees. Anyway, the patent only had 3 years or so to run when the project was started, and we got the machine working a few months, in fact, before the end of the patent. So it was rather good timing, though entirely coincidental. I hadn't planned it that way at all. Okay, here's a picture of one of the commercial RepRaps. That's one made by Prusa Research in the Czech Republic from Joe Prusa, whom I know well. They're quite a big 3D printing company. In fact, I think it may be the case that they actually ship more 3D printers than any other company in the world. They may not have the highest monetary income because some machines are much more expensive, and I'll come to the cost of the machines in a moment. But certainly RepRap type 3D printers are certainly the most widely produced, as I just indicated. And in fact, the way that Joe does it is that he has a big printer farm, warehouses full of his own machines, printing out parts for copies of those machines. And that's just one corridor in the Prusa RepRap self-replicating manufacturing workshop, consisting of a very large number of RepRap machines. I mentioned cost. As I'm sure you're all aware, you can buy a 3D printer these days for $500–600 or so. I also mentioned at the beginning of this talk that the cost of the very first machine that we bought was about $50,000. So we reduced the cost of the machines of this project by a factor of 100, not by 100%, by a factor of 100. By running this project and putting these machines out there. As I say, the one that we bought, the cheaper one that we bought, was pretty much the lowest cost one you could get at the time in about 2002, 2003. Okay, well, anyone with a plant can grow a seed for a friend, ignoring seed patents. And so anybody with a RepRap can make another RepRap for a friend. And we can talk a little bit more about this sort of self-replicating idea in a minute or two in the questions, if you like. But I wanted to say a few words about the whole principle. I'm sure it's a principle you're familiar with, the whole principle of economies of scale, which is an idea that goes back a long way in the history of economic thought. And it's illustrated by these two pictures here. On the left, we have a traditional blacksmith's forge with the blacksmith beating out a horseshoe. And every village would have one of these to make hinges and door knockers and horseshoes, of course, and that sort of thing for use by everybody else around. On the right is a picture of a 19th century iron foundry, which is essentially solving the same sorts of problem, but at a much, much bigger scale. And the classic idea of economies of scale is that if you bring together a large number of people in a big space to perform an operation with a market of a large number of people, you can make objects very, very cheaply because you save a lot on various functions which can be spread across the entire operation. For example, you have one person who's responsible for maintaining all the furnaces, as opposed to one person in the blacksmith's forge who's responsible for operating the bellows to keep his one small furnace going, and so on. So economies of scale mean efficiency. But something that's not so often realized is the fact that economies of scale go into reverse. So for example, if we can get a technology cheap and simple enough, it tends to put economies of scale backwards. So again, looking at the 19th century, top left there, we've got a picture of a 19th century laundry. People of our great-grandparents' generation used to pack up all their laundry in a bag and send it off to the town laundry, and it would come back 2 or 3 days later all clean and possibly even ironed. And that was an example of economies of scale over everybody doing it themselves. Now, of course, these days hardly anybody does that because we all have a robot in the kitchen, like the one on the right, to do the job for us. And the reason we can do that is because all we have to do is to open that door at the front, chuck in the clothes, put a bit of detergent and a bit of fabric conditioner in the top, press a button, and it goes away and does the entire job for us. So the amount of thought, attention, and application required to operate it is negligible, and it does the same job. And rather interestingly, we're perfectly prepared to spend the money on having that machine, even though it probably spends 90 to 95% of its time idle, just sitting there, not even washing our clothes. And of course, this also applies to other technologies. The electricity that's conveying my words and image to you at the moment is largely generated by objects like the one on the bottom left there. But increasingly, everybody is running their own little power station with solar panels on their roof. And in fact, the first stage of that journey of voice and picture that I just mentioned is being conveyed to you by the solar panels that are above my head as I speak. And so distribution of a technology, as opposed to economies of scale, gives convenience. Obviously, you don't have to worry about sending stuff to the town laundry. Possibly if the power station goes offline, you manage to keep going if you have your own source of electricity, depending on how it's organized. But it certainly also gives robustness. If the water supply to the town laundry fails, everybody has dirty clothes. If your water supply fails, you can go and knock on your neighbor's door and say, would you mind if I borrowed your washing machine? We haven't got any water. And the chances are, if they're nice people, they'll say yes. So you get more robustness if you distribute anything than having it as a single point of failure centralized service. Okay, well, some other examples of that. Today, everybody listening to me now, you will have your own CD pressing plant, your own photographic laboratory, and your own printing press. Of course, they don't look like any of those traditional versions of those objects. They look like a streaming service on your phone. The phone is also the photographic lab, and possibly you've got an inkjet printer sitting on a desk somewhere that is your version of the printing press. So though the actual technology has changed, you've taken those previously centralized economies of scale type technologies and brought them into your own home. Now, if you're going to do that, why not everybody have their own factory? And if you're going to have everybody having your own factory, then let's make it a factory that makes more factories. So if one person's got one, they can make another factory for somebody else. So self-replication is inherently redistributive because it allows people to share any piece of technology if it's self-replicating. And that, of course, includes the things that, in the case of a 3D printer that's self-replicating, the printer prints as well as the machine itself. And it tends to work against the concentration of wealth because it allows people to acquire the ability to make things for themselves and thereby avoiding the expense of having to pay somebody else to do it. And I said, this is a tendency, it's not a universal rule. Anyway, that's really all I wanted to say by way of introduction. If you want to know a little bit more, point your phones at that thing on the screen and it'll take you to the website and you can find out. So thank you all very much.
Thank you very much, Dr. Bowyer. That was great. So I know I have a bunch of questions that I want to ask, but I first want to give some opportunities to members of the audience.
Sure.
So, yeah, so I suppose if you have a question, I guess there's either you can just chime in or raise your hand, or however you want to go about doing that.
So I have just one quick question. When you said, like, I do a fair amount of work with the open source enterprise on campus, and a lot of that, all the work that we publish is on a wiki.
Yeah.
And you said those really didn't exist when you originally made your project open source. So what did it look like to do something open source in the early 2000s, and how has that changed?
Well, to answer your second question first, how it's changed is we established a RepRap wiki when it became possible to do so. And indeed, that URL, which I've just put up on the screen, will take you to that wiki. But as you say, we didn't have it at the beginning. At the very beginning, because I was at university, I could simply put all the project data and documentation so on up on my own university's website. And that was fairly straightforward. And then after that, we established a blog using Google, in fact, Google's system for where anybody can set up their own blog on Google. And so we used to put a lot of the information out on that blog, as well as putting it on the university website. So that was two of the three stages. And then the third stage, as I say, was to establish a wiki. Once that software for that became available, and we used and still use the software that was developed to put out Wikipedia. And we also run a forum where people can discuss technology and how to solve problems and so on that as well. And that was the last thing that we set up. I mentioned the blog. An aspect of this that we thought was rather important was to get any ideas that we had for how to make the machine work out as early as possible into the public domain. And the reason for that, of course, is that if anything is in the public domain, it cannot then subsequently be patented. And the advantage from that respect of a blog is that everything is dated, and I'm guessing nobody's really going to seriously try to argue with the dates that are on a blog being run by Google. So that meant that we could get pieces of technology that we came up with to solve the problem of making the machine work out with a date stamp on them effectively, and that stopped people trying to patent a lot of them, or if they did patent them, then the patents weren't valid because of prior art. So that was the sort of history of how we put the distribution of it together.
Hi, Dr. Bowyer. Can you hear me?
I can hear someone talking, but they're very, very faint.
Oh, shoot. Can you hear me now?
Hardly. Hang on, I'll turn the volume up a bit.
Hello?
Hello.
Hey.
Hang on, I'll just turn my volume up.
Okay, perfect. So I just had a quick question for you. What are you excited for about the future of RepRap? What are some of the big things that you see happening in the future?
Well, perhaps I can start by a failure. Something that I was surprised hasn't really happened. Well, it happened a little bit, but not nearly so much. When I started the project, I thought that very quickly we were going to get the ability to 3D print plastic parts with electrical conductors embedded in them. And I thought that that would be a very, very powerful addition to the technology of 3D printing, and something that would allow people to build electronics into three-dimensional mechanical objects. And that in itself would be very useful. And in fact, I had a couple of research students who worked on that very problem, and successfully they managed to make systems that worked, in that they basically managed to print three-dimensional plastic objects with a very low temperature melting point solder embedded in them to form electrical circuitry. But that doesn't seem to be taken off in the general world of 3D printing. A lot of the machines that have been developed don't seem to. You can buy electrically conducting filament, which you can put through a 3D printer. It tends to have a fairly high resistance, certainly compared to a metal. But nonetheless, I would have thought that there would be really strong concentration on getting that working and doing interesting things with it. But that doesn't really seem to happen. For example, I'm sure there are far more machines out there that can do multiple colors, that can do an electrical conductor and an electrical insulator. And that's what I'd be excited to see, is someone taking that idea forward and really getting an easy to use, straightforward system for printing high conductivity materials along with conventional plastics in a single object, so that we can make three-dimensional electrical circuitry and also make things like crude electric motors and so on. As I say, it's happened a little bit, but I'd expect that to have taken, as it were, to taken the world by storm, and it doesn't seem to have, and I don't know why.
Awesome. Well, thank you. Shane, there's your next project.
Dr. Bowyer, we got a question in the chat from Wilson, so I'll just read it off real quick.
Yeah.
Has there been any significant? Oops.
Sorry, that was my clock
2:30.
chiming a half hour. Beg your pardon.
So, has there been any significant pushback to open source in your work? And have there been cases where that was well-founded pushback? Why or why not?
Yes, one. It was very friendly, but it was also significant. Stratasys, whom I mentioned had the original technology that we use patented, also have a trademark on the abbreviation FDM for fused deposition modeling. And we thought that that was just a general technical term that we used throughout the project to describe what it was that we were actually doing. And I got a very nice letter from a Stratasys lawyer, and I mean nice, I'm not being sarcastic here. He was very polite, and he said, look, we're perfectly happy for you to carry on your project, but please don't use our trademark term. And so we did a global edit, I having invented the term FFF to be an exact equivalent, fused filament fabrication. The problem just went away. So really, that's the only thing that anybody ever complained or worried about as far as the project was concerned. And as I say, it literally took an hour in the morning to fix the problem. So that was that. Sorry, the question was it well-founded pushback? Yes, it was well-founded. They really did have that trademark, so fair enough.
Any other questions from the audience? All right, I guess I'm going to dig into my bank of questions here then. So let me see here. Yeah, so one of the topics my students are currently writing about in the 3D printing class and kind of researching is if open source is better for society than a model that protects intellectual property like patents and things like that. And so I'm curious if you could give them some help. Do you think open source is always the answer, or do you think things like patents sometimes have their place?
I think that in any sphere of anything, it's always the case that nothing is always the answer. So no, but let me first of all say what my own experience of working is, and then let me broaden that out to actually answer the question. I run a little company that's in a way based on RepRap, though we mainly act as consultants to other people, and sometimes we act as expert witnesses in legal cases and various other things like that. And that's how we make money. And everything in that company that we use, both hardware and software, is open source. The entire company runs on Linux, on computers. All the CAD software we use is open source, both for electronics and for mechanical design. And also all the software that we use is all open source as well. So I think I'm correct when I say that we literally do not have a single paid for software license anywhere. And we run it legitimately. We don't use pirated software or anything like that. Anyway, so that's our own case. The company is run by my daughter and me, and we can run a commercial company, would seem successfully, entirely upon that basis. So that's, if you like, an existence proof that it can be done. Is it a good or a bad thing in general? Well, I actually would like to propose that we keep patent law exactly the same, except for one tiny, tiny change. And the tiny change is a single box on the patent application form, which you check. And against that box, it says, make this an open patent. And what does that mean? I'll come to that in a moment. But what I want to do is I want to keep patent law identical all over the world to what it is now, except with that one tiny addition. If you don't check that box and you've got an invention and you patent it, you get your patent in the normal way. You perhaps choose to license it with a big company, whatever it might be, however you want to exploit it. Everything stays exactly the same. But if you do check that box, what happens is this. Your patent, as all patents are, is published, and then anybody can make your invention. You're not protected from people copying it. But what you are protected from is taxation. So if you put out an open patent, what that would mean is that anybody can make this patent as a commercial activity or not. If they do it as a commercial activity and sell it, they'll have to pay taxes on that activity. But if you and you alone as the patent holder choose to make the object that you've patented or idea that you've patented, then you will be able to do that tax-free for the duration of the patent. Now, if you think what would happen if that were the case, a number of things will be a result. One is that the authorities, the government or whatever, will almost certainly make more in tax income than they would have otherwise if it was a good idea, because you've got 10 companies all making this thing, all paying taxes, except for one of them, which is you yourself, and you are not paying taxes. You've got an advantage for having your patent because you don't get to pay taxes on your work, whereas everybody else does. So you can sell perhaps slightly more cheaply than they can as a consequence of that. And finally, one of the aspects of patents that's really difficult, particularly for sole inventors and small people who are running perhaps a very tiny business, is that you can't afford the legal outlay required if you want to protect your patent against someone who's copying it. You can't go and try and sue a really big company because they're going to be able to afford great big lawyers and you can only afford a tiny, tiny lawyer. So that's an aspect of patenting which is intrinsically unfair. But if you went down my route, you wouldn't have to bother about protecting your patent because you'd just have the tax-free status of running your idea when everybody else would have to pay taxes on it. So effectively, the taxation authorities are going to be running the policing of your advantage for you automatically, and they'll do that because they want the tax from all these other companies who are making your idea. So anyway, that's what I propose as a very small change to patent law, which would allow it to be much more accessible to small people, small inventors. But I mean, if you're a giant pharmaceutical company, you can choose to do this as well, whereupon, of course, all your rival pharmaceutical companies can make your drug, but you alone don't get to pay patents, pay the taxes on your exploitation of it. You know, if you're Pfizer, you don't pay, but if you're I can't think of another pharmaceutical company now. Someone will be able to think of one. Whatever, pharmaceutical company X, they do have to pay. Anyway, so do I think patents are a bad idea? I suppose on balance I do, because they seem like a slightly strange thing. We normally regard any sort of monopoly as being a bad thing, and a patent, of course, does give you a monopoly. There's a famous book which of course is free to download because it's against the whole idea of patents and copyrights, called Against Intellectual Monopoly. That makes a pretty strong case that these things are not such a good idea for the world. But you have to be practical about this sort of thing, particularly if you want to make changes happen. The advantage of the scheme that I've just proposed is that nobody can complain about it because you're not taking anybody's patent away, and they can still have the patent they used to have if they wanted to. So it's not something that's subtracting anything from anybody's abilities to do as they please.
Cool. Okay. That's yeah, I like the idea of not having a huge disruptive change. So that's pretty clever.
Yeah. And incidentally, you could do the same thing for copyright, of course.
Sure.
And it will work just as well in that. If you're an author, you can put your book out with an open copyright or whatever we would want to call it. Then other companies can print your book, but only you don't get to pay tax when the book is sold.
So I have this kind of another question that I was just thinking of. It's mostly a for me question. So we've all heard Sir Isaac Newton's quote, "If I have seen further, it is by standing on the shoulders of giants." And so this is cool for me because you're sort of one of the giant shoulders that I stood on when I was doing my graduate work. But I'm curious, who are some of your giants?
Oh gosh, it's more giants of attitude than giants of technical input, I think. I mean, there are people whom I think are extraordinary, but just going back to 3D printing, it was only after I thought about the project and decided to start it that I looked into the people who had created the technology. And indeed it was, although this is not quite the case, but I'm going to say it anyway, then I'll correct myself. It's almost the case that I didn't even know about that joke that I mentioned back in the early 1970s when I started the project. The very first appearance of the whole idea in public. In fact, that's not true. When I rediscovered that, I suddenly realized that I'd read that very column when I was a postgraduate student, 30 years before. So I did know it at some level in my mind. But yes, the guy who wrote those columns, David Jones, I think probably one of the giants on which I stood, because he spent decades writing jokes, and he invented, among other things, the fullerenes. That's to say, Buckminster fullerene, the carbon-60 molecule. He figured that was going to be possible before anybody had actually made it. Didn't get the Nobel Prize for it, somebody else did, but he was the first person to think of it. He invented the idea of noise cancellation, the thing that's used all over the place in noise-cancelling headphones. And thousands of other inventions that he came up with. He reckoned towards the end of his life that about 18 to 20% of the things that he published as jokes actually turned into real pieces of technology. And if 1 in 5 of your ideas makes a really world-changing piece of technology, then I think that's pretty good going. Yes, an extraordinary man. And as I say, perhaps he's one of the giants upon whose shoulders I stood.
And his name again was? I gotta write it down.
David Jones, yes.
David Jones.
He used to write under the pen name Daedalus, like, the Icarus's wings, the maker of Icarus's wings.
Okay, so I mean, the other thing that we see a lot is that you can't really make money off of open source stuff, which we probably both know is not true. But I'm wondering if you could speak to that, if it is possible to pay the bills while making open source contributions.
Well, Shane, suppose you wanted to set up a factory making teaspoons. Now, lots of human beings need teaspoons, and you can make teaspoons and sell them to companies and stores and so on all over the country, or possibly all over the world. there's nothing, a teaspoon is effectively an open source object because there's no intellectual property in a teaspoon. And yet people make teaspoons and they sell them without any difficulty whatsoever, and they make a profit doing so. Indeed, when you think about it, virtually every product is implicitly open source because it's out of patent. The vast majority of things that are made and sold without any sort of serious, solid intellectual property associated with them at all. You can't patent the idea of an internal combustion engine, you can't patent the idea of a television camera, and so on and so forth. So almost every piece of engineering production activity is done without solid, serious, actual, this technology is patented type protection. So it's demonstrably the case that companies can make money by doing things without intellectual property protection. As I say, the vast majority of products are in precisely that category. Now, of course, people do patent things and make them and sell them. There was the guy who invented the Black & Decker workmate bench, you know, and that sort of thing, and that was patented for a while. And obviously, he sold it to Black & Decker, and they paid him royalties, and he got to be wealthy. One of the famous ones is the person who invented cat's eyes, the things that go in the road to retroreflect headlights back to the driver. That made the person who invented them very, very rich because they sold the rights to build the objects to basically everybody who was laying roads. So it's certainly something that can be done. You don't have to have intellectual property protection in order to make money, as is demonstrated by the fact that lots of things that get sold, indeed the vast majority of things that get sold, don't have that protection.
Sure. So you've helped trigger a huge new era of making and engineering. So with all sorts of projects depending on open source 3D printing. So are there any open source hardware projects that you're particularly fond of?
Well, yes, there are several. One particular, if we count a molecule as hardware, there's a project to open source the entire production chain for making insulin. Which would allow anybody to set up production of insulin without any sort of intellectual property. But the idea of insulin itself, of course, can't be patented because it goes back way more than 19 years. But various bits of and pieces of the technology required to produce it are protected. So there's this idea that we make a completely open source production mechanism for making insulin, and I think that would be an extremely good idea if it were to be done. And you can see once that was established that you could do it for a very large number of drugs as well as insulin. Again, the vast majority of drugs that are used are out of patent rather than in patent, in just the same way that teaspoons are out of patent. But one of the interesting aspects of that, again, which comes to this question which I mentioned when I was giving my little talk at the beginning about different patent laws in different jurisdictions. Certainly in the UK and Europe, if you manufacture something that's patented for your own use without the idea of selling it or making any sort of profit from it, then you don't have to pay a royalty. I can take a patented object, and if I make one and stick it in my workshop and just use it myself, as long as I don't make money out of it, which includes using it to make other things to make money, as long as I don't make money out of it, I don't have to pay any royalty. Now, imagine an open source drug manufacturing machine which could be installed in a patient's home and that would manufacture the drugs they required to keep them well. Then presumably in principle, even if those drugs themselves were patented, the fact that the person was making them themselves would mean that in Europe and the UK, as I say, at least, they wouldn't have to pay any royalties on that. And that would be a rather interesting position to be in, I think. So that's just one example.
Yeah, it's I've followed all the open source insulin projects as well. It's
Yeah, but
Yeah.
yeah, and open source chemical manufacture and doing things like open source gene sequencing and that sort of thing. There's a great deal. As we know, a lot of these processes that deal with very small quantities of very complicated materials, like DNA, for example, are highly robotic in the commercial field, and pretty much all of those robotic mechanisms are amenable to being manufactured using open source techniques, indeed using 3D printing techniques. They're basically just Cartesian robots that move stuff around. So that's something that I think everybody who's listening to me understands pretty well.
And so if you personally had infinite budget, staff, and expertise, what would you want to be tackling in 2022?
Oh, if I had infinite budget, staff, and expertise, I'd obviously the project that I would instigate would be to give myself eternal life, because I've got infinite resources to do it. And then once I'd done that, it wouldn't matter what order I did projects in, because I'd have infinite amount of time to finish them all. Sorry, that was a rather facetious answer.
No, that works.
You put the infinites in the question, which is clearly impossible.
So,
if I had a lot of budget, what would I do with a very large budget? I don't know. Some of those things I think in the medical field. I think opening up a lot of medical equipment, drug manufacture, and the drugs themselves, and so on. I think that will be a very useful thing to do with a significant amount of resources, if one had them.
So you said that it was an uncharacteristically noble thought for you to think to open source the RepRap project. So were you not involved with open source like work before RepRap, or were you? Or
I was just being a bit self-deprecating, really, but
gotcha.
Yes and no. Open source software, yes. I'd used Linux for years and years, and indeed made tiny contributions to open source software in various places. I've written various video filters for camera video applications and this sort of thing, which are open source. So software, yes, but I'd never done an open source hardware project. And indeed, when we started RepRap, there was quite a bit of, we talked about pushback earlier on, there was actually quite a bit of pushback from the open source software community saying, oh, this is not for hardware, this is just for software. Nobody says that now, and everybody's forgotten that they said it when they did. But there was a certain, open source is for bits, not for machines, they said, at which I would always respond, well, these days, all machines are ultimately bits, because of course they consist of design files on a computer. So that's the point at which the open source applies. So to answer your question, I was in a very limited way involved in the creation of open source software. I was more involved in the use of open source software because I simply used it for my own work. But as far as open source hardware was concerned, no, not until we started the project itself.
Have you ever used the Google engram viewer?
I know about it, but I'm not used it.
Yeah, so I'll share real quick this guy. It was just kind of something I shared with my class too. So this is just showing the usage of the term open source hardware in books and literature. And so you track right there, 2009, when you published a RepRap paper, and I mean it already kind of had that slope up, but it just carried on. And it's actually interesting to see this huge dip after 2016. So I'm not sure what happened there. But yeah.
So how many years is that dip? Is that just a dip because the data isn't available? It was 2016. What's the date of the last point on the graph?
2018.
So two years later, right? Okay.
Yeah.
Yeah. Okay. Oh, I don't know.
Yeah, but I you just kind of look at before that 2009 point, or looks about like 2000, open source hardware wasn't even, like you said, a thing that people mention, right? It wasn't really a term.
It'd be very interesting to have a similar graph for open source software and superimpose the two on top of each other. First of all, to see if the dip also curved the open source software, and secondly, to see how much ahead of the hardware curve the software curve was.
Yeah, here I can bring it back up here.
Oh, you've got that as well. Oh, great.
Yeah, here I can. Here we go. Yeah, so there is.
Oh, right. Okay.
That dip is there.
Oh yes, it's the same pattern. Almost, well, apart from the little hiccup at the end, but that's because it's had more time to display more detailed characteristics. But that's very interesting. I wonder if the dip is simply caused by the fact that everybody's used to the idea, and so people don't bother to talk about it.
Sure, it's kind of gone past that novelty point a little bit.
Yes, exactly. Where people feel obliged to mention it. Oh, this is a new thing, I've got to talk about it. It may have some analogies with the hype curve in that it's something that people talk about a lot, but then when everybody gets used to it, it isn't talked about so much. I don't know.
Sure. Yeah, so there, you were totally in that that, I don't want to say that hot spot for when open source hardware was getting big, and then having the ability to distributively manufacture things just caused that to skyrocket. So
yeah.
Well, it's a 10:55, and I know I blabbered a lot. But
I think I even more than you, much more than you.
Sure. So do we have any last question that's anyone's thinking of?
Oh, someone called Nathan. I apologize. I didn't see his question in the chat. When building the RepRap project, how much time and effort was put into tuning and setting aspects of the printer compared to the construction design of the printer itself? I'm guessing now, because this is not something which I can speak to accurately because I don't have the figures with me, but I would say about 30% of the time was tuning and redesign. Once we got something pretty much working, doing the improvements needed to get it working so that we could call it a working machine. It was a prototype, it always was, but I'd say about 70% design and manufacture and 30% subsequent tuning. But that's a guess on my part. Don't quote that as being a figure which has any sort of rigor associated with its accuracy.
Yeah, I almost always try to hold myself and tell my students that it's going to be, you should budget, if you have a whole year, you should budget probably about half the year for your design and half the year for fixing and tuning and all that stuff. Yeah. I usually go 50-50 because a lot of inexperienced students will say, oh, I'll use the whole year to design it and I'll put it together in the last month and then it's going to work, but it's almost never the case.
It never does. No, that is true. Yes. And to a certain extent that comes down to experience. I don't want to claim an enormous level of experience. On the contrary, when I started out on this, I knew less about 3D printing than everybody in the 3D printing industry. But I did have some experiences as a design engineer and a researcher in the fields of engineering that were required to build the machine. And so
uh-oh.
But yeah.
Oh, you froze up for like the last 20 seconds.
Am I live? I'm live to me now. Can you hear me?
Yep, you're live now. Yeah, it was just like the last 20 seconds.
All right. Okay. I mean, I can probably pretend to freeze, but like that, but just to cause trouble.
Well, it's 10:58 here. What? It's almost 3 o'clock your time. Haven't quite heard
4
your,
o'clock,
your
yep.
bell chime yet. Yeah. Well, so thank you so much for agreeing to do this talk.
Well, thank you for
appreciate it.
inviting me. It's been a great pleasure. Thank you all very much.
All right. So Dr. Boyer, I'm going to be in contact with you. I'm not sure what it's going to be, but we're going to send you some nice goodies. So I'm going to see if I can get your mailing address. So
But don't feel obliged. They'll be
Well,
more than welcome, of course, but don't feel obliged.
Certainly.
Thank you very much. Thank you.
Yep. All right. And I'll also send you this recording because you said you wanted to be able to share it. So I will
Yes,
send
if
it
we
over.
can, that would be good. Thank you.
Very good. All right.
Okay. Well, good morning to you all.
Yeah.
Goodbye.
See you. Thank you again.
Bye.